The strangest thing about beta decay is that it depends on this particle, if we can call it that, called a neutrino. This is what Fermi and before him Wolfgang Pauli came up with. Well, let's talk about particles that we can actually detect. Proton, you can deflect a proton and see it hit a target. You can deflect an electron and see it hit a target. A neutron, it's easier to theorize its existence because it's very close to the mass of a proton. And when you look at isotopes, you can come up with the idea of a neutron. But detecting a neutron is pretty hard as well. But a neutrino, what is a neutrino? Well, a photon has no mass, but you can detect it because it's light. But a neutrino is theorized to have no mass. That's where it gets its idea of a neutrino. I don't really know how related to a neutron it really is, but that's the name that we have to use. And we don't know how to detect it. So, what's the idea? Where do we come up with that? Well, there's something about the beta decay spectrum that says there must be something else. Well, why does it have to be just one particle? Could it be a series of particles rather than three particles? That's a good question. Well, in 1956, they came up with an experiment that they claim detects a neutrino. Now, look at how hard this is. This is how hard it is to come up with this idea of a neutrino. So it's an indirect method. So what do we really know that a neutrino exists? This is how they did it. They had a very high energy system that created what they thought were neutrinos by colliding atoms together or particles together. And then they sent these neutrinos through 20 tons of water. In this 20 tons of water, well, why choose water? That's a very unusual thing. Well, here's why they chose that. What they're trying to do is create beta plus decay, which is very, very hard. So there you've got something that's very hard to do. So in this 20 tons of water, the H, or the proton of the hydrogen nucleus, is not really attached very well. And that's why that they say that the ionization of water naturally occurs into hydrogen and hydroxide ions. Hydrogen proton and a hydroxide negative ion. So this naturally occurs so that hydrogens are ready to go to be hit independently with that proton. So what are we trying to do? Well, the theory is that with these neutrinos, we're going to hit a proton, and that proton is going to cause a positron, which is the idea of beta plus decay. That positron then will quickly annihilate into an electron. Annihilate with an electron, and then will produce a photon or high energy photon, which is a gamma ray, which can be detected. So really all we're doing is looking at photons, and somehow we're telling ourselves that that tells us that there are neutrinos. So without any math, how do we figure this out? How do we really justify it? And that was my idea for going into Fermi's decay theory. Now, do we know anything else about neutrinos? Well, neutrinos can have a uh, neutrino and an antineutrino. Now, since they're neutral charged, that doesn't mean the charge changes, but it says the spin changes. Now, how can that be? An electron has spin of 1/2, but an electron can take on two types of spin. But the theory is that the neutrino has spin, but it can't change. So, where are we going with this? I'm going to take one more look at that spectrum, give some more thoughts on it, and then we'll see where we are headed next in this journey. Here's the electron energy spectrum from beta decay. Now I showed this once before, but let's dive into it a little deeper. This E max is what the energy level would be of an electron if there weren't any other particles. So that's way out here on the graph. This E electron is the energy of the electron. This E sub nu, it's a Greek letter nu, which stands for neutrino, and it's got a greater energy span than this one. And notice the energy levels of the electron are lower than the neutrino. Now, this peak doesn't mean higher energy, that means more electrons. So the most number of electrons are down at this really low energy level compared to what the electron would be. So, what happens at this point? Well, at this point, there's very few or no electrons. So, what does that mean? Where did all the energy go? Well, the energy was taken up by the neutrino here, but there's very few of those where that actually occurred. So there's all kinds of balances of the electron and the neutrino. Now, how could this be? Why wouldn't it just be a simple balance where the electron would be lowered to this level and the neutrino would occupy this energy range? Well, one of the things is the neutrino, its mass is not constant. In other words, there's more than one flavor of neutrinos. There's a muon and a tau neutrino. Now, am I just trying to confuse you with all this? It says that how can these other neutrinos be created when I've just said it was the electron neutrino? Well, what happens is this is the theory, this is current theory, is that when the original decay occurs, now what caused the original decay? The original decay was caused by a boson, which was a weak boson. So you have a force interaction with this boson. I'll show another picture here in a little bit, but that weak boson creates an electron neutrino. That everyone seems to agree on that part. But as it's radiating, that during the beta decay, it's also recognized that the neutron oscillates. So it oscillates between an electron, a muon, and a tau. All these different Greek letters that we use to represent all these different types or different flavors of neutrinos. It's not something you taste, it's just a different category of neutrinos, and flavor happens to be the word that was chosen. So, if that's the case, then that means that there's different energies of neutrinos going out there because these different flavors have different masses. and that means that there's going to be a different amount of energy as all this stuff goes on. So this is a very shaky theory as I even explain it, because it's hard to comprehend why that would be, why it wouldn't just be a nice, neat electron energy and the rest of it would be absorbed by the neutrino energy. Let's review something here about how we go from a neutron to a proton, and in this decay process, we have an electron and an anti-electron neutrino. Here's a down quark. Here's an up quark. We won't focus really on what those things are right now. But anyway, when we go from one to the other, we emit a weak boson, and it's called a weak minus boson because we're actually pulling away a minus symbol, which creates a positive uh, proton up here. So when this thing happens, notice it in this picture, they show that they simultaneously turn into an electron and an antineutrino. This arrow going back this way shows that we're going backwards in time. Isn't that an interesting idea? But that's how these antiparticles are described. So, since it's almost simultaneously, sometimes the electron's created before the antineutrino, sometimes the antineutrino is created before the electron. Anyway, because of all these differences, the energy balance between the two is going to be changing as this whole creation process occurs. So maybe that will put some pieces together yet. But the neutrino is only created easily in the lab by this decay process of whatever radioactive substance we happen to be using. Carbon 14, uranium, various different things could be used. But now we have to figure out what in the heck is the math that can predict what the balancing act between these two values, the electron and the neutrino. And I hope that this Fermi theory is going to take care of that. Is this enough symbols for you? Oh my gosh. Well, let's start walking through these different things. N and M, capital N and M. Notice that N has this little S thing. The S stands for state, and the M has a sigma. So we want to keep the difference between this kind of state and that kind of state. The N state happens to go along with electrons, and the M state happens to go along with the antineutrino. So remember, there's the electron and antineutrino that are radiated along with the change from a neutron into a proton. I think this is the letter Psi. Anyway, this has an S for states, and this has a phi for states, lowercase phi. These are the quantum states. And here are the quantum state amplitudes. So this A and this psi and this B and this phi, those kind of go together because these are the amplitudes and these are the quantum states. N and M can only have values of 1 and 0. So we've got a whole series of different states that the electron or the antineutrino might occupy. But each one can only have 1 or 0 and that's mostly due to the idea of the Pauli exclusion principle. So let's see, I've got all that laid out. Okay, I think I've done all that. Now, there's another variable called rho, and this rho can equal a 1 if if the heavy particle is a neutron, and rho equals -1 if the particle happens to be a proton. Now, don't worry about this -1. At first, that seems wrong. Seems like the proton ought to be +0 and the neutron ought to be 0 or something like that. But there's no way we could get the math to work that way. So, finally, and this is the title of this video about the Hamiltonian is going to be split into two pieces. One is a Hamiltonian for the heavy particle, which is a neutron and a proton, and the Hamiltonian of the lightweight particle. That's an L right there, not a 1. So that's a lightweight particle. And that's the electron and the neutrino. Now that I've introduced the symbols that we're going to work with, let's move on, and I'm actually going to refer us to the text from Fermi's theory. So let's see if we can make some sense out of some of these symbols used together. Okay, from the text, they're talking about how these n values can only occupy a 1 or a 0 for each state because of the Pauli exclusion principle. Now, the operators, which I called the amplitude, was either a sub s or an a sub s with a little asterisk here. And the asterisk means the complex conjugate of that. Complex conjugate, if you multiply it together with its other side of the world, then you multiply these two and you get a real number. This being a complex number, then you multiply the two and you get a real number. They're defined in the following manner. Notice I've got an a sub s here, and then on the right side of the equation, I've got this -1 to the power of all of these n's. Now, the n's can be 1s or 0s all the way through, but it's going to come up with either a -1 or a 1 when we're all done with it. And then finally, 1 minus n, capital N sub s, which is the occupation number of the very last state in all of this series. Now, what is this thing? This capital psi value with all these n's? That means that this is a state function, and these are all the quantities that make up the determining variables for that function. And notice it's over here too. So all we've done is replace the a sub s with this value, which is either going to be, in this case, it's going to be 1 minus n sub s, or if the negative sign applies, then that means it's going to be n sub s minus 1. For a conjugate variable, we're going to come up, notice we've still got that -1 value all the way up to n sub s minus 1, and the n sub s here is not the same as 1 minus n sub s. Now, all of this put together means that this value is going to be the creation operator, and this is going to be the annihilation operator. Annihilation is associated with the 1 minus n sub s, and this is the creation operator, which just gives us n sub s. In a like manner, for the b sub s and the m occupation numbers, we have this relation, and rather than using the function psi, because it might not be that, here's the function pi and capital pi here, and here are the M values, and notice how similar all this construction is. The B is for the creation and annihilation of the neutrino, whereas the A's were the annihilation and creation operators for the electron. Here's the title of the video, The Construction of the Hamiltonian Function. Now, let's come all the way down here and look at the N and the P. The N and the P represent the energy operators of the neutron and the proton. It's not the same N occupation values that had all these states, 1 plus all the way up to S, but this is the neutron operator and the proton operator. So let's look at the relationship. If you remember, the neutron operator has a value where if rho is equal to 1, we get the neutron. So 1 plus 1 times 1/2 gives me a neutron value, and 1 minus 1 gives me 0, so the proton falls out. If the rho value is minus 1, then this goes to 0, and the N value also goes to 0, so the neutron falls apart. And then here we go 1 minus a minus 1, that'll give us 2 times 1/2, which gives me the proton. Note that this is for the Hamiltonian for the heavy particles. Looks pretty simple. So let's go ahead and accept that as we can. The Hamiltonian for the lightweight particles, remember this H stands for Hamiltonian. Well, over here we have H is going to stand for the energy of the electrons in that state, and the K is going to stand for the energy of the neutrino in that state. And notice we sum over all of these different things from 0 to S and 0 to sigma for the neutrino side of this picture. Now I'm going to introduce two operators. One is Q and one is the complex conjugate of Q. And notice these are very simple 2 by 2 matrices where the 1 shows up at a different place. This is 1 shows up in the second position of the first row. Here it shows up in the second position of the first column. First row, first column. And we'll see how that all plays out now down here. If your mind is capturing all this, this was that 2 by 2 matrix, which is multiplied times A, which had to do with the creation and annihilation operator. This was actually the annihilation operator, and this was the annihilation operator of the neutrino. This the electron, this the neutrino. Same place in this case, down here. Down here, we're doing the creation of electron and the creation of a neutrino, antineutrino. So this is the process of going from a neutron into a proton, and this is the process of going from a proton into a neutron. As I continued to look at this theory that Fermi wrote, I realized I was in over my head. And this idea of teaching is learning, also teaching is finding out how far behind you might be. So I'm going to have to close this out and say that until I understand quantum field theory, which requires a high level quantum mechanics preparation, I can't go any further with Fermi's theory, even though he did this thing in 1934. So somehow between the 1920s and 1934, there was a lot of activity. So those 10 years there brought up the ability to talk about this neutrino and all this stuff. So I'm going to have to hold off on this, and we will come back to this topic later. I hope this was informative, at least up to the point that I gave it. And if not, I apologize.